It's right at 9 o'clock. Okay, good morning, everybody. Let's go. All right, so just a reminder, quick bit of housekeeping. No class Wednesday, right? Get to Cancun or wherever you're going to go to, or stay in Fort Worth. If you need to contact me for any reason over the next few days, just give me a bit of time to respond. I'm headed to South Africa tonight, so when I can get onto the internet or Wi-Fi is when I will get back. We have a dark screen on the left. I have to figure this out. On to start. Maybe. Okay, whilst that is starting up, because I do want both sides of the room to be able to see that. That comes on in 1 second. It's telling me that it's working. Look like it. Let me just preface this morning. I think I've made this comment before. So this is the most complicated material we're going to cover in the course, right? That's not to scare you in any way or anything like that, but this is a little bit of atmospheric chemistry. And I will be very specific here as I go through this, what I expect you to be able to talk to me about and explain and articulate in the exam, right? I know if you've taken a look at chapter 5, quite a bit of material in there again that deals with the chemistry of the stratosphere and how this plays out in terms of ozone. But I'll be quite specific here as we go through. Less promising. Okay. There it is. All right. Let me get here for a second. Okay, so this morning what we're going to do is I'm going to kind of unravel and reveal the story about stratospheric ozone depletion, how that came to be. I'm going to update you with what's going on right now as of yesterday at the South Pole. Most of this discussion here hinges on Antarctica, focuses on the South Pole, right? And we'll examine why that is the case. But just as a quick recap, remember we're looking at the vertical distribution of ozone. Make the point that low-level tropospheric ozone and stratospheric ozone are chemically identical, right? One is formed through the emission of pollutants. This is the low-level ozone. You're emitting nitrogen oxides. The oxygen gets disassociated with the nitrogen and forms O3. And in the stratosphere, ozone forms and is destroyed naturally, right? Through this cycle, where you've got sunlight splitting O2 into oxygens, oxygens combining O2 to form O3, and the sunlight continues the destruction by taking O3 and disassociating that into O and O2, right? So that is a natural formation and destruction process. Is everybody good with that, right? In the stratosphere. So let's leave the lower atmosphere behind for a second. Okay. I think what's quite interesting here is when you look at that vertical distribution of ozone, right? So that curve we've just seen where you see that big bulge in the stratosphere. Yeah. And we cannot do this. But if we were able to do this, if we were able to take all of that ozone in the stratosphere and collapse it down and squeeze it down, right? And compress it into a layer, it would form a layer that is just 3 millimeters thick, right? That's one big take-home message. And what I'm trying to explain in this diagram here. We can't do that because ozone is distributed throughout the stratosphere. But if we could compress it, all of that ozone would form a very thin layer, about 3 millimeters thick, right? About the thickness of 2 pennies. That is what keeps life on planet Earth, or one of the reasons why we're here, or are able to live here, okay, is because of that. And you'll see why in just a second. How do we measure ozone? How do we express it? We express it using this thing called the Dobson unit. You can see that on the screen here, the Dobson unit. That's named after the scientist who came up with the instrument to measure stratospheric ozone. And the one number I do want you to remember here from the outset is 300, right? 300 Dobson units is equal to about 3 millimeters of ozone, which is how much ozone there is in the stratosphere. right? So again, if we were to take that ozone in the stratosphere and compress it down into a thick layer that was just 2 pennies high, that would be 3 millimeters. That's the equivalent of 300 Dobson units. So the reason why I want you to remember that, everybody, that 300 Dobson units is that is what we consider the background concentration of stratospheric ozone, 300 Dobson units. Make sense? So just keep that in the back of your mind. If we talk about average stratospheric ozone, we're talking about 300 Dobson units. All right, please, everybody, just fire questions at me as we go through this, because again, this is going to get a little more complicated. What does ozone do? Well, what ozone does in the stratosphere, and the reason why we use that phrase "good up high," is that it absorbs ultraviolet radiation. Right? That's the bottom line. Now, we haven't introduced the electromagnetic spectrum yet and how that all works, but for now, right? Let me just say that the vast majority of the energy that we get from the sun, if you went outside right now and stood outside in the sun, right? That energy from the sun is coming to us in the form of radiation, right? Some of that radiation is long wave radiation, like infrared, and we'll explain that when we get to climate change. A whole bunch of it is visible light, okay? Some of it is ultraviolet, and there's a little bit of other. So if you guys, heaven forbid, if you break your ankle or something and you go to the doctor, they take an X-ray, right? What are they doing? They're firing very short, high energy radiation into your leg, and you get to see the X-ray, right? We don't worry about that type of radiation when we talk about this class in the atmosphere. We look at infrared, visible, and ultraviolet. And this morning's conversation focuses almost exclusively on ultraviolet, right? That is high energy, shortwave radiation that comes from the sun. So what this diagram is showing you here is that actually the ultraviolet radiation that comes from the sun, there are 3 different types, okay? There's UVA, which is the radiation that's very close to the energy that we get from the sun in terms of visible light, right? And a lot of that UVA gets through to the surface of the Earth. Then there's UVB and UVC. So as you move from the right there, from UVA to UVC, the intensity of the radiation increases, right? So UVC is shortwave, high energy, more dangerous radiation. For now, that's a good way to just think about it, right? So UVC is really dangerous. And what's critical is that the ozone layer absorbs all of that, right? So in the natural formation and destruction of ozone, when I said that ozone absorbs energy from the sun and breaks apart the ozone into O and O2, that's what's going on. The ultraviolet radiation comes on in, it hits the ozone, and the ozone absorbs that energy, and in doing that, breaks itself apart into oxygens and O2s, and then it reforms, right? So this part here on the left, this UVC, that is ozone absorbing all of the high energy, dangerous UVC. It gets almost all of the UVB, it lets a little bit through, and it lets quite a chunk of the UVA through. So that's why if you're smart and you go to the beach, you go to the pharmacy and you need to buy sunscreen, right? And you rub sunscreen on, and that has a protection factor. Does that make sense? You know that, right? And so that protection factor will help absorb the UVA rays that are coming through and reduce the damage, right? So as you go from right to left there, the damage increases on ecosystems, on your skin, and so on. All good. So that's the function of ozone, right? Ozone absorbs harmful ultraviolet radiation, right? It keeps our planet livable. All right, cool. So here's how the story unfolded, right? How did we come to find out about ozone in the stratosphere? So in 1974, the paper comes out in the journal called Nature, right? So that's one of the most prestigious journals in science. And it's published by these 2 guys, Mario Molina and F. Sherwood Rowland. And they published this really important, quite controversial paper, okay, that was looking at the ability of chlorine to destroy ozone. That was the central premise, right? The British Antarctic Survey in Antarctica was sending back data that was looking quite tricky, that ozone was being depleted, and there was a lot of work done in the late 60s and early 70s about the depletion of ozone. we didn't remotely fully understand the story here, but these two scientists showed unequivocally that chlorine, right, was the culprit in destroying ozone. Chlorine actually as part of a substance called CFCs. You've probably heard of CFCs, chlorofluorocarbons. Here it's chlorofluoromethanes. It's all part of the same family, right? So CFCs were substances that were developed in the late 50s, early 60s, predominantly by DuPont Chemical. And CFCs were thought to be totally harmless. They're used in refrigerants, they're used in propellants, they're used in deodorant spray, all sorts of uses for CFCs. And they were seen to be pretty impressive because they were colorless, they were odorless, they didn't think they did anything. They were sort of viewed as benign to the environment, right? These two guys come along in 74 and say, not so fast. The CFCs that are being emitted into the atmosphere, the C part, the chlorine, is the culprit in destroying ozone. DuPont Chemical took them to court. They said this is absolute nonsense, but within a couple of short years, it was shown pretty clearly that the chlorine was the culprit. And so then in 1995, those two guys, along with the person whose name you may recognize from chapter 1, they shared the Nobel Prize in Chemistry, right? Creating work on the destruction of ozone by chlorine. Paul Crutzen is the guy on the left. He was the one who coined the term the Anthropocene in 2002. So yeah, there's no Nobel Prize for environmental science, but there kind of is when you're working on chemistry, right? So that's how this unfolded. Okay. So here we go. If you have coffee, I would take one sip now, or maybe a big one. So we're going to do two things here, right? My challenge always, folks, at this point, is that this is a bit of a chicken and egg scenario. Okay. So here's how I do it. I'm going to introduce you here to what is known as the chlorine cycle. Okay? I need you to understand this, right? And the chlorine cycle explains how chlorine destroys ozone. Okay? So that's kind of the egg. Part is there's a second part to this chlorine cycle that I'm going to mention, and then we're just going to park and come back to, because the second part explains what's going on over the South Pole. And that's the most important part in the world in terms of ozone destruction, right? So there's two parts. That's the chicken part. The chlorine cycle I'll introduce you to first. We'll explain all that, and then we'll go and look at what's going on at the South Pole. It only makes sense to do it that way because we can't, well, I suppose we could go to the South Pole, and then you're probably thinking, well, how does this all work, right? So that's where we're going to go. So here's the chlorine cycle. Okay. I know this font is pretty small on a slide here. I don't like putting small font on a slide. I've got it on here just to keep me honest, but this reproduces just fine in the book, and you should have it if you've got your PDF up in front. I can see you're annotating here on the left here, so that works well on a screen like that. So let me just walk you through the chlorine cycle. Step 1, bottom left here. Okay, we emit the CFCs. Right, and I've tried to draw that here. So here's the chlorine, the carbon in the center, and the fluorine, right? And this is just one of what we call ODSs, ozone depleting substances, right? So the CFC that's in a spray can, a refrigerant, a propellant, whatever, gets emitted into the atmosphere, right? As a CFC molecule. Make sense? Perfect. Step 2, UV radiation strikes that CFC and splits apart and takes off the chlorines and frees up the chlorines that you see right over here. Okay, that's a free chlorine. Make sense? Now, that happens around the world. That happens all over in the atmosphere. Okay, the destruction of the CFC to free up the chlorine. Okay. Now, at that point, that free chlorine can go and attack an ozone. And it does so, but it does so in, relatively speaking, very small quantities. Why? Because most of the chlorine here that is freed up by the sunlight actually then goes and forms a variety of other things that we collectively call reactive gases, right? We also refer to those as reservoir gases. Here's the two most important ones. So the chlorine here can hop up here and form HCl. See, the Cl joins with a hydrogen to form that HCl. What's HCl? Hydrogen chloride, right? The other important one is the chlorine will hop on here and join up with a nitrogen and 3 oxygens, right? And there's the chlorine. And that forms ClO, NO2. That's chlorine nitrate. Okay, those are the two most important reservoir gases. And think of them like that, folks. Think of them as reservoirs, right? Just sitting there waiting. They don't, those two gases, the hydrogen chloride and the chlorine nitrate, do not destroy the ozone. Okay, they don't. They're reservoir gases. The chlorine that is freed up by the sunlight splitting apart the CFCs, that chlorine, the vast majority of it, hops into these two forms, chlorine nitrate and hydrogen chloride. Does that make sense? And those two reservoir gases make their way slowly to the polar regions. Why? Because that's how the air works on the planet. The tropics heat up, the poles are cold, and the tropics are continually sending out warm wind to the poles, and the poles are sending out cold wind back. So there's this continual cycling of wind between the tropics and the poles. And those two gases that you see here, the chlorine nitrate and the hydrogen chloride, end up getting transported to the poles. Okay, I need to stop there. Everybody on board? Okay, shaking left to right. No, let's stop there and make sure we clear. Let's go here.
After the UV radiation strikes the CDC.
So good question. So the chlorine will join with these two. The chlorine will join with a hydrogen atom to form hydrogen chloride. That's one thing it can do, right? So this is the key question right here. And the second thing it can do is it can join up with this one here. It can join up with nitrogen and 3 oxygens, NO3, right? And so when you just look at the chemistry here, this is a chlorine that's been freed up here, and it's ClO, NO2. That's the chlorine nitrate. So those are the two compounds that are formed from that freeing up of the chlorine. It's a great question. That's the key. Does that make sense?
Yes, sir.
Okay, good.
Is it the free chlorine that's destroying the ozone layer? Is
Yes.
it the gases?
No, another great. And so this is this is the chicken and egg, right? This is what's so tricky about this. It's the free chlorine, but we're not there yet. Okay, that's another good question. Both of you guys have hit the nail right on the head here. It is the Cl that destroys the ozone, right? But not quite yet. Question?
What happens after it?
What happens when the chlorine,
Like what happens after that?
when it joins up and forms the hydrogen chloride and chlorine nitrate? Then those reservoir gases slowly but surely drift their way down towards the polar regions, right? They stay in the stratosphere and they move down towards the polar regions. And to come back to your question up here, sorry, I don't know your name.
Hayden?
Hayden. So to come back to you, at this point, this chlorine can destroy ozone, right? If there's a little bit of it in that space, right? So here's how this looks. Let's just take off the reservoir gases for a second. I see you, Riley. I'll get you in a sec. Let's take off the reservoir gases that are making their way down to the poles. So how does this work, right? Here's how it works. The chlorine that is freed up attacks an ozone, right? It steals this one oxygen. It leaves behind the O2. Remember, ozone is 3. So that chlorine steals one oxygen, leaving behind an O2, right? That creates this little thing here called the ClO. That's chlorine monoxide. Okay. Now you've destroyed an ozone molecule. Does everybody see that? The chlorine steals one oxygen off the ozone, leaving behind an O2. That creates the chlorine monoxide. Okay. Then an O2 comes along and says, you know what? I think I'll have that oxygen hanging out on the chlorine monoxide. And so an O2 comes along here, steals this oxygen, and frees up the chlorine again. That cycle is the catalytic cycle that goes on. The free chlorine destroys an ozone, leaving behind an O and an O2. The ClO, chlorine monoxide, looks around and goes, okay, let's see what's going on here. An O2 comes and steals that oxygen, right, to free up the chlorine again. Okay, so that's the catalytic cycle. Okay, everybody with me? Yeah, right at the back.
So the main thing about the single chlorine is that we're left with a bunch of O2 and then we don't have any O2.
That's the bottom line, right? You're left with a bunch of O2s. Okay, right?
So basically, just for clarification, once the CL splits from the original molecule, it can take two routes, either gas or.
Okay, so I couldn't have said that any better, right? That's probably how I should phrase it. So when the Cl is split apart by the sunlight, it's got one of two routes, okay? It can either find an ozone to destroy, that's what you need to know there, or, and this is the majority of what happens, it forms one of these two reservoir gases, hydrogen chloride and chlorine nitrate. Your first question. That makes sense to everybody? Yeah.
So we want a
In the stratosphere, we want as much O3 as we can. Absolutely. So remember, we've got this natural background cycle going on of sunlight splitting O3 into O's and O2s, and O2s joining with O's to form O3. That's going on naturally. Here's the human fingerprint. The human fingerprint is CFCs emitted into the atmosphere. CFCs break down. Chlorine is freed up. It'll either destroy an ozone or it'll go into a reservoir gas. Now, to get back to Hayden's question, when that chlorine destroys ozone, it does so, but it does so in relatively small amounts. It's almost not really noticeable, okay? The big stuff is going on over Antarctica, which is what we're going to get to next. Right. All right. Oh, great question. Is the chlorines destroying the ozone more quick? Hold on to that until we look at what's going on in over Antarctica. Great question. Yeah. Love it. Love it, love it, love it. Okay. So yeah, so this is the ramification. The ramification is as we destroy ozones by releasing this chlorine, we have more oxygens, which was your question right here. We have more oxygens relative to ozone, and that just simply lets in more ultraviolet radiation. That's the environmental issue. All right, so let's go to Antarctica. This is the second part. We're making good time. So I'll ask you a little bit about the chlorine cycle. Nothing more complicated than that, right? If I was to say, okay, when what's the chemical culprit? It's CFC. How does the chlorine get freed up? It gets split apart by sunlight. What, as Riley said, what are one of the two parts it can take? It can destroy ozone, but generally the vast majority of it goes into these background reservoir gases, chlorine, nitrate, and hydrogen. So why do we look at Antarctica as the most problematic? And I'll talk a little bit about the Arctic region as well. All right, so the British Antarctic Survey, along with other countries, but predominantly British Antarctic Survey, from the 1950s and 1960s, were sending up weather balloons, like you see in the photograph on the right here. Okay. And they send up these weather balloons to every 12 hours to look at the chemistry of the atmosphere above the South Pole, right? The temperature, the makeup of the chemistry, the ozone, everything like that, right? And from the 1970s, the late 1970s, and into the early 80s, they noticed, and the names of these scientists aren't critical, but these three scientists noticed that there was a continual depletion of ozone over the South Pole, right? And it happened at a specific time of year. And by 1985, they were so confident in this trend of declining ozone that they published this paper showing, and now we're looking down on the South Pole. This isn't a great image, but I've decided to show it because it's from the original paper. So this is looking down on the South Pole, and this big red blob here is the hole in the ozone layer. Here's South Africa. Okay, here's Australia, and here's the southern tip of South America. By 1985, they were confident, and they said, okay, scientific community, here we are. We have a hole in the ozone layer, right? And this is actually the data from the paper. And all I want you to notice here is this is 1960, 1970, 1980 here. And you can see the trend going downwards. The lines show the confidence intervals around the measurements. But when you look at the trend, here's 1960s. And just look here, folks, where that number is on that graph, right? This number here is 300. Remember that? That's your average background stratospheric ozone level. By the time they get to 1985 right here, those levels are down at 200, right over here. Okay. In 1985, they published this paper, and the world goes, wait a minute, what's going on here? Right? We're seeing this catastrophic decline in stratospheric ozone from 300 Dobson units to under 200 Dobson units. Not a great mathematician, but that's about 33%, right, of a depletion of stratospheric ozone. It completely confused people as to why it was going on over the South Pole. And as we'll see in just a second, why it was happening so quickly, right? Front page news around the world. Okay, experts raise alarm over rising UV rays. Ozone hole raising concern for scientists say worst ozone hole stirs healthcare. Right. So this was right at the forefront of the media in the 1980s. The hole in the ozone layer, well before your time. Right. So whilst ABBA was producing great music, the hole in the ozone layer was beginning to open up, and it really caught people's attention. So the rest of this morning, the next 20 minutes or so, we're going to look at how this happens. Right, why this happens. Any questions? All good. Okay, so here you're looking at, so all our conversation here will be focused on Antarctica for the moment, because that's where the ozone hole is the biggest, and there's a reason why, right? So we're looking down here, here's Antarctica, right? This is normal ozone levels. This is the ozone level, the ozone hole in the spring. Now, when you see spring here, don't think March. Okay, you need to think August, September. Right? Everything's upside down. Well, I'd like to think it's the correct way around down there, but it's all different down there, right? Does that make sense? Okay. And this blue here, just look at the scale, guys. Anything in green or the very, very light blues are what we consider normal ozone levels, about 300 Dobson units. This big blue blob that's sitting there is in the region of 120 to 200. The purples are very, very low, right? It looks like a hole. It's not really a hole, okay? It's a thinning of ozone, all right? It's not that the ozone hole opens up and there's no ozone, because that would be really tricky, right? But it's a thinning from 300 to about 220. Anything less than 220 Dobson units, that's considered significant depletion of the ozone layer. Visually, does that make sense? Okay, cool. A couple of ways to look at it, right? So here what I'm showing you is the data from the South Pole from 1975 through to 2019. And I can update this in a little bit, okay? So this shows the ozone hole. Now just look at the dates here, very important. This is the minimum ozone layer, 21 September to 16 of October. There's a reason why I love teaching this course in the fall, because this is the week. What's the date today? The 11th. This is the week that the ozone layer is at its thinnest, right? Right now over Antarctica, the hole is at its biggest, okay? This week. There's a reason why. So this shows 1979. This is the 225. You can see by 1994, we're down at 92. There's some variation here, right? Again, we'll explain why in just a little bit. And you can see, you know, if you take, I don't know, 2004 onwards, there might be an indication here that there's an upward trend there, meaning the ozone hole is beginning to recover a little bit, but there's some caveats to that, which I'll also mention. The little diagram here on the bottom left here, that's the 220 Dobson unit line. So yeah, it says hole there, right? But that's the thinning. Does everybody see that, what we're trying to show here? This is 1985, so that's 79, 81, 2, 3. So there's 1985 where they published the paper on the hole in the ozone layer right there. Any questions on that, right? That's the thickness or the thinness of the ozone layer. Here's another way to look at it. This is exactly the same data, but it's expressed in terms of the size, the area of the hole. Maybe that is a bit easier for you to get your head around. I know it is for me, right? Instead of thinking of a thinning, just think of how big that hole is. So you can see over the last, I don't know, 30 years, and I've drawn these lines in myself on the data. This line here is the size of North America. This line here is the size of Antarctica. You can see the size of the ozone hole has generally been up in the 24 to 25 million square kilometer range. 2019 was a very, very small ozone hole. I'll make a comment as to why, and then we'll look at what 2020 is in just a second. Right? All good? Okay, cool. Give you a sense of scale here. This is the ozone hole. This was October 2020. It was a very large ozone hole. There's Antarctica. And if you're having a tough time thinking about the size of Antarctica, there's the actual size of Antarctica plotted next to the actual size of the United States. This is actually a really cool website. Okay, it's called The Actual Size Of. And if you ever have to do anything geographical, it's really neat, right? Because you know, when you look at a map of the world, depending on the projection, sometimes Antarctica looks like, you know, the largest continent in the world, or Greenland looks enormous. This is very cool. This website allows you to highlight a country and drag them down to the equator, so you can actually see the actual size of it, right? So again, there's Antarctica there. The hole in 2020 was bigger than Antarctica, right? And comfortably bigger than the size of the US. All good. All right. Okay. You know what? I'm gonna skip that. Right. Let's skip that and see if we can tie it in again. All right. So, what are we looking at here? This is the South Pole again, right? We're looking right down on the South Pole, Australia, South America, Cape Town. Okay. These black dots. Okay. These black dots are. It's a computer simulation, but it's essentially what happens in reality. For this particular date, there's nothing unique about September the 21st, 1992 in particular. The black dots represent the trajectories of weather balloons over a 24-hour period every time you see a dot, right? So in other words, let's just go up here. Here's a weather balloon released here. That's 24 hours later. That's 48 hours later. That's 72 hours later. Each one of those dots represents a 24-hour increment. Just showing the trajectory of weather balloons. If you release those balloons all along the line of longitude. You notice. This is exactly what happens. Notice on those weather balloons. What can you say about the trajectory of the weather balloons? They're doing what? They're moving clockwise. And not only are they moving clockwise there, they're going in circles, right? They're going in circles clockwise around. Oh, okay. Everybody see that? That's exactly what happens over the South Pole, right? Over the South Pole is this gigantic blob of really cold air, okay? And there is one on the North Pole as well, but it's especially well developed over the South Pole. The air over the South Pole is significantly colder than the air over the North Pole. Who wants to have an attempt to explain why? If you can answer that question, then I'll be really impressed. Why is this big blob of air over the South Pole colder than over the North Pole? And there's a critical implication of that, do you think? Why is the South Pole air so much colder than the North Pole? No. Good attempt. Is it the axis? No. Physical geography of South Pole versus North Pole. Okay. Oh. Someone's going to get this. Yeah. No, it's not elevation. Something to do with the ground or non-ground. What's the South Pole covered with? What's Antarctica covered with? Ice, snow, glaciers. It's a continent, right? It's a continent that's bigger than the United States, covered with ice and glaciers. And the North Pole is what? Is it a continent? What is it? What's the North Pole? Ocean, right? Sea ice that grows in the winter and shrinks in the summer, right? There's bits of Canada and Russia there, but the North Pole isn't a continent. The North Pole's water. And would you all agree that water heats up more slowly, cools down more slowly than land, right? If you don't believe me, just move to Wichita, Kansas and send a family member to San Francisco. Wichita, Kansas and San Francisco have exactly the same average annual temperature of about 68 degrees Fahrenheit. But I can bet you your closets look very different. Why? Because Wichita heats up during the summer and cools down dramatically in the winter. San Fran is moderated by the ocean. So the North Pole is sea ice and ocean, and therefore the atmosphere sitting above the North Pole is relatively much warmer than the atmosphere sitting over Antarctica. Antarctica has this huge big blob of really freezing cold air, right? And we call that blob the circumpolar vortex. Okay. Now I know it's been a few years, but I don't know if any of you have seen the movie March of the Penguins. Anybody seen that movie, March of the Penguins? Yeah, great film, right? And when March of the Penguins happens, what happens is towards the end of March, the month March? Where does the sun go if you're sitting in the South Pole? Well, it disappears below the horizon, right? And the South Pole, right at the South Pole, gets plunged into 24 hours of darkness, right? And the North Pole gets put into 24 hours of sunlight. One of the things I really want to do is play golf under the midnight sun. Okay. Scandinavia. So March of the Penguins happens, and those poor male penguins are sitting with their eggs, and they all huddle in this big cluster while the ladies go up and chill and do their thing. And the sun goes down, and the egg gets colder and colder and colder and colder, right? And we call that the circumpolar vortex, this big freezing cold blob of air moving counterclockwise. Okay, why are we going on about this circumpolar vortex? Because in that circumpolar vortex is where the chemical reactions take place that destroy ozone. So this one I'll just skip over. This just shows you the march of the sun. If you're sitting at the South Pole, right, in February, you're in daylight, 24, this is hours, 24 hours of daylight. You get to March, the sun begins to go down. From the end of April through to early August, it's totally dark. 24 hours of darkness over the South Pole. Okay? And then what happens? Then these things appear. And these are what we call polar stratospheric clouds, PSCs, polar stratospheric clouds. And it's these clouds, everyone, that are critical to the destruction of ozone. Right? Question?
Is this one that has 24 hours of darkness?
Yeah.
And what is that?
So at the end of March, the sun goes down and then it gets plunged into southern hemisphere winter. Okay. So folks, these aren't clouds that you and I see outside on a daily basis, right? These are formed in the stratosphere. From there's tiny, tiny little ice crystals, but they're also made up of something else called nitric acid. Okay. So they're incredibly unique clouds. They don't produce rain or anything like that. And they can only form when temperatures drop below minus 78 degrees Celsius. That's another number I just want you to have in the back of your mind, right? So the sun goes down, the temperatures get cold, they get colder and colder and colder, and eventually those temperatures can drop to minus 78 Celsius. When that happens, these clouds form, okay? And it's on these clouds that the reactions take place. And in fact, remember those two things, the hydrogen chloride and the chlorine nitrate, those two reservoir gases that have been transported to the poles? Those are the gases that hop onto the clouds, which I'll explain now in a second. PSCs, polar stratospheric clouds. Yeah, okay. So this is the diagram that I try to come up with to show you the temperature difference between the Arctic and the Antarctic. So just look at this for a second. We've got months here on the bottom. This is the Antarctic winter, May, June, July, August, September, October. We're now just to the right of this graph. The solid blue line shows the long-term average. That's all you need to focus on. That's the long-term average of temperature over the South Pole. The red line refers to the northern hemisphere winter, right? So this is where we're headed now, November, December, January, February, March. That's our winter. And that red line shows the average temperature over the North Pole. The horizontal gray line here is the minus 78 degree critical cutoff for polar stratospheric clouds. What do you notice, right? Notice how much lower the temperature is over the South Pole and how much longer that temperature stays below that critical temperature that the polar stratospheric clouds can form. So look here, if you look at the North Pole, this little area here where the red line drops below the critical -78, it's just a little bit and for not very long. The South Pole, it's the entire winter, right? So over the South Pole, it's much colder and you get polar stratospheric clouds developing much more rapidly. Okay? All right, so let me just let this run. This is July. It's dark. And then August, and then September. I'll let this just run a couple of times. And then October. So as you get into the blues and the purples here, this is the opening up of the ozone hole over the South Pole, right? Or the thinning of stratospheric ozone. I'll let it run one more time, and then we'll go into the final explanation here. So here it is in the dark. It's just this lightish blue. And then watch how quickly the colors begin to change in August. This is what really stung the scientists, just how quickly stratospheric ozone is depleted. All right. One more little chemical cycle, okay? One more. Here is how the reactions on the clouds work. Let me go back a second and let me address Hayden's question right at the outset. The CFCs are released, the chlorine is freed. That free chlorine, it's the Cl that destroys the ozone. That free chlorine can do a little bit, but most of it ends up as hydrochloric acid and hydrogen chloride and chlorine nitrate. So here's how it works. And along the top here, I've drawn these all out. There's a hydrogen, there's a chlorine, a nitrogen, an oxygen, Cl2, there's your HNO3, HCl. I'm going to explain all of these now, right? So here's the first step in the recipe of ozone loss over Antarctica. So just scribble that down, phrase it like that. I'm going to ask you, explain the recipe for ozone loss over Antarctica. This is it, okay? You could do a precursor to that to say you've got to have the CFCs emitted and the chlorine's broken apart and the reservoir gases are formed. But here's the recipe, right? Temperature goes below -78 and these polar stratospheric clouds form, the PSCs. So this is step one, the PSC form. And those two reservoir gases, the hydrogen chloride and the chlorine nitrate, right? The two that you asked about right here up front, okay? Those two reservoir gases that have been transported down to the poles, they hop onto the cloud. And that's the only place they can react is on that cloud, okay? So the hydrogen chloride, the HCl, and the ClNO2 hop onto those clouds and they react on that cloud. And the reaction is the chlorine here from the HCl and the chlorine here from the chlorine nitrate, they join together to form Cl2. Not individual Cls, but Cl2. That cannot destroy ozone yet, right? Cl2. And look what's left behind. A hydrogen, a nitrogen, and 3 oxygens, HNO3. What's that? Nitric acid. That's what makes up the majority of the cloud, that nitric acid. So yeah, you've got these little ice crystals, and then the nitric acid is there. Then what happens is this Cl, the Cl2, the molecular chlorine, those Cls hop off the cloud. Here they are. So folks, this is all happening in the dark. The Cls, the Cl2s hop off the clouds, and the HNO3 stay on the clouds. And it just evaporates out later, right? It's all in the dark. These are dark reactions. So now the atmosphere over Antarctica is primed with Cl2. There's no destruction of ozone happening yet. And then what happens in early August? What peaks its little head above the horizon? The sun. That sun comes up very quickly. And here's the final piece of the puzzle. The sun's rays in step 4 strikes the Cl2 and breaks them apart into Cls. And that launches the chlorine cycle, right? That gets back to Hayden's question at the beginning. Sun comes up, strikes those Cl2s, the Cl2s become Cls, and the atmosphere goes crazy. The Cls hunt out a little ozone, pulls the oxygen off, forms an oxygen atom. That ozone finds another, that chlorine cycle kicks in. That's the catalytic reaction. And that's what stunned the scientists, is that nothing happens until the sun comes up, and then the ozone just gets destroyed very, very rapidly. Does that make sense? So there's the chicken and egg scenario, right? The CFCs are released, the CL's freed up. It does a little bit of destruction around the world, but very little because that CL's tied up in the reservoir gases. The reservoir gases are transported to the polar region, much more widespread over the South Pole because the temperatures are so much colder. So you have many more polar stratospheric clouds developing. And then those reservoir gases hop onto the clouds, they react. The CL2 hops off and it just waits and it waits and it waits until the sun comes up. And then the CL is free. Yes.
So which one of the acid?
So HNO3, right? This is down here. HNO3 is the nitric acid, and that stays on the cloud. Great question. Until the sun comes up, and then those polar stratospheric clouds evaporate, and the nitric acid just falls out. It's in relatively low concentration.
So they evaporate because they're made
Yes. Yeah. So here is what's going on right now. I just cut and pasted this morning. Okay. So what are we looking at? All you need to look at here is, so this is all the data from 1979. This is January through December. The black solid line here is the average, and then the different grays just sort of envelope all of the data. The blue line is 2020, the red line is 2021 until this morning at 8 a.m. over the South Pole. Okay, what do you notice, right? So you can see that January, February, March, the ozone levels here are around about 250, 220, 250. The sun goes down here. This is all of the buildup of ozone. Okay. CL is building up. Nothing happens until the sun comes up here at the end of July, early August. And there's the depletion of ozone, right? All the way down. You can see here that 2020 and 2021 are big ozone holes, or it's thinned dramatically, right? Because the polar stratospheric clouds and the circumpolar vortex have just been so cold, right? So that shows the speed at which the ozone hole is depleted. Here's the diagram from before, showing minimum ozone over the South Pole. There was 2019. 2019 was a much warmer year over the South Pole. Here was 2020. 2020 was a catastrophically cold southern circumpolar vortex. 21 looks like it's going to be the same thing. Right? So a much bigger ozone hole. And if you plot it in terms of the area, you can see 2019 was a very small one. Here's 2020, right? So there's a fair amount of variation there and fluctuation that worries people in terms of how quickly this is potentially recovering.
So is the size of the hole dependent on the temperature?
Yeah, the size of the hole is really dependent on the temperature and, of course, how much chlorine is in the atmosphere. But as I'll wrap up in just a couple of minutes here, that amount of chlorine has declined over the last 20 years. So that's, you know, that's the positive hole. So 2020, very long, very deep winter over the South Pole, much colder, well below the -78, lots of polar stratospheric clouds, and the depleted ozone layer. Here's the final slide, everybody. And again, I know this is quite a lot coming at you, and in the next study guide, I will be super, super specific here, okay? What have we done about this? Okay, here's an environmental success story, I think, potentially, right? So what are we looking at here? So this shows the two most important reservoir gases in the atmosphere. The bottom one is chlorine nitrate, right? There's our friend ClONO2. The red one is HCl, right? Hydrogen chloride. And those two combined are what you see in the blue triangles, right? So the blue triangles are just sort of a broad, what we call free chlorine, right? Or available chlorine. But just focus on the reds and the greens, okay? The environmental success story is when the world came together in 1987 to sign a binding agreement called the Montreal Protocol. I don't know if you've heard of that. It was signed in the city of Montreal in Canada, 1987. Remember, 1985, right here, they're publishing the hole in the ozone layer. They know it's chlorine. 1987, the world comes together and says, we have to start reducing and ultimately banning these ozone depleting substances like CFCs and bromine and so on. And so that happens, and it goes through a number of revisions, 1992, 1997, 2002. The point here is that the world finally comes together and says, enough, we have to ban these substances that contain chlorine because that is what's destroying the ozone. right? And do we see any results? Well, absolutely we do. Yeah, we've got a big hole this year, but when you look at this trend over here, this shows chlorine in the atmosphere actually peaks at about 1995. And we're starting to see a very gradual decline in the concentrations of chlorine over the stratosphere, right? It's slow going because chlorine stays in the atmosphere for a very long period of time, and then eventually will settle itself out. The hope is that by 2050, because we've banned CFCs, that this curve will just keep going down. Chlorine will keep going down, and here we will be 2050, and chlorine will be so low that ozone levels will have recovered over the South Pole. Right? Of course, the health implications are simply that you're letting so much more ultraviolet rays in. Questions? You probably deserve a Wednesday off after that. Okay. All right. Good. Be safe. Have a great break. And I will see you next week.